Hey students, let's continue our discussion of the mechanical energy. In the last video, I've introduced kinetic energy, Ke, and gravitational potential energy to you. And this time, I would like to introduce elastic potential energy, elastic PE to you. And it is the energy stored in an elastic object when it is stretched, compressed, or bent. So for the normal case here, if we do not stretch it, compress it, or bend it, then the elastic P stored in this spring would be 0. And if we stretch it, then it will gain elastic PE. And if we even stretch it in a greater extent, then it will gain even more elastic PE. So it's the same case for compressing the spring. If we compress it, then it will also gain elastic PE. And if the spring is more compressed, then it will gain even more elastic PE. So, although it is out of syllabus for the formula of elastic PE, but I will still like to show you. So, remind that this is RC, out of syllabus. I mean, the concept here is in the syllabus. You need to know it. But for the formula here, for the elastic PE, which is 1 over 2 kx squared. The k here is a constant, is a spring constant for that spring. So if we are using the same spring, then the spring constant here is the same. But for this x is about the distance of stretching or compressing the spring. So if we stretch or if we compress the spring with a greater distance, then here x is greater. So that here the whole thing, the elastic PE would also be greater. That means that if we compress it more or we stretch it more, then the elastic PE would increase, would be bigger. So I think this formula may help you understand the concept of stretching it, compressing it, and its relation with the elastic PE here. So if we don't stretch it, if we don't compress it, just leave it here, just leave the spring here, then it would not have any elastic PE. And I would like to emphasize potential energy, this word. And why is it called potential energy? You can imagine in this way. If we compress it, compress the object here, and then it will store elastic PE. What if we release it? I think it's a very typical case in our daily life. If we compress it with an object attached here, if we release it after the compression, it would start moving, right? So that what's the energy conservation here? The elastic PE, after we release it, it will be converted into kinetic energy so that it moves. And I think this is easy to understand. Another typical example for this elastic PE would be shooting with a bow. So if you have played with shooting with a bow, then it would be very easier for you to understand that. And if you haven't, for example, when the bowstring is released, if you release it, then what will happen? The arrow will move, right? So here, I mean the arrow will be released and it start moving. So elastic PE after you release the bowstring, the elastic PE stored in the bowstring will be converted into what? It would be converted into the Ke of the arrow. Because when before you release it, you are actually stretching the bowstring. It's a string. And after you release it, it's no longer being stretched. And it will restore to its original position so that the arrow would gain the Ke, would gain energy from that bowstring. And the PE stored in the bowstring will be converted into the Ke of the arrow so that the arrow would move. And after we introduced the elastic PE and we also introduced the Ke and gravitational PE already in the last video, so this time the last part of the mechanical energy would be exactly mechanical energy. Why do we call it mechanical energy for this chapter is because actually the total mechanical energy for an object is the sum of its Ke and also its Pe. Using this figure as an example, if you apply a force to that object, to the block here, and it moves under gravity, if the velocity of this block change, and if the vertical position of this block also change, then the work done by the force would be the change in Ke of the block plus the change in Pe of the block. So that here, the work done by the force, which is Fs, because it also travels a distance s, right? And for this energy gained by the block here due to this applied force would be the change in Ke plus the change in Pe, which the change in Ke can be represented by 1 over 2 m and then v squared minus u squared, because the change in Ke is 1 over 2 m v squared minus 1 over 2 m u squared. And v is the final v velocity and u is the initial velocity, and plus the change in Pe, which is the change in gravitational Pe, and is mgh. Remember, this is not s, this is h, because we are talking about the change in the vertical position, the height. And we can illustrate with example 6 here. So for example 6, it's the same case. We apply a force of 20 Newton on this object, on this block, and this block accelerates so that it gains Ke. And it also moves with a vertical displacement so that it also gained gravitational Pe. And how to find this Ke gain is easy. The Ke gain here, this delta is the change, right? So it gains Ke. The gain in Ke would be 1 over 2 mv squared. mv squared minus 1 over 2 mu squared. And just substitute the value back to the equation here, which is the mass is 1 kg. So it's 1. And the final velocity is 10 meter per second. So it's 10 square here. And because it's at rest initially, so the initial velocity is 0. So u here is 0. So the whole thing here is 0. So it's minus 0. So you will get the value for the Ke gain to be 50 joule. And the second part, it asks for the traveling distance s when the block reaches a speed of 10 meters per second, which is the same case here, because it goes from rest to 10 meters per second. And then how to find this distance s? Remember, you did work. Work is done to this block, which should be the same as the change in Ke plus the change in Pe for this block, so that you can list the relationship between W, Ke, and Pe, where the work done should be the same as the change in Ke plus the change in Pe, which is the same case introduced above. And then the work done here is Fs. If you wonder what is the F, it's 20 Newton. If you wonder what is the S, yes, you need to find this S. And then the change in Ke here you have calculated already in part A, which is 50. And what is the change in Pe? The change in Pe should be mgh, right? But you don't have the h. But you can find the h by yourself. First, we write down mg first. What is the h here? You know this S, and you know the inclination, which is 10 degrees here, so that you can find the h by using this s sine 10 degrees. It's just trigonometry. I think this should be covered in the part of resultant force already. And even if you don't know it, you can still use trigonometry to find this h, just using sine theta. So you need to find the s. You just change the subject to be the s and find the answers by yourself. And for part C and part D, after you obtain the value of s, it's easy because work done is just Fs, and change in PE is just mgh, where h is related to s. You know it. So after you find the s, the whole question could be solved. And this is the end for this part of mechanical energy. And this is also the end of this video.